Hello class again and welcome to this particular video, and in here we're going to build on where we stopped on our previous video, where we will be focusing on position time graphs that are curved in nature. Based on what we talked about on our previous video, we looked at various forms of curves that happens on a position time graph. Position time graph we know of is that we have a position measured in meters and is in the east direction, and this is plotted alongside or against our time in seconds. And take note of one case scenario where we have our A to be decreasing in terms of specifically velocity, not speed, because speed is a scalar quantity or velocity is a vector quantity. And so when you take the instantaneous velocity, we see that it is positive, but it is decreasing all the way to the zero mark, which is in this case represented as the curve A. Now on the other part here, we have a different scenario where we're starting at zero velocity, which is in this case horizontal slope, and then it is curving way up. And you know that by your instantaneous velocity, it's actually showing that we are having positive values increasing for our specific velocity. So this is expressed as B. And take note of our last part where we're starting at a particular height and you are actually going down all the way to the zero mark. And this is similar to when you kick a ball from a specific height and it is starting at the horizontal velocity, and then it makes its arc way down. This shows that we're starting at zero velocity, and then or specifically we have a specific velocity and the velocity just increases, in this particular case having a negative value but increasing in terms of the steepness based on the instantaneous velocity, and that goes to our specific ground region, which is right over here. So these are the three case scenarios, and what we have come to the conclusion is that the velocity is non-constant either for C, for B, or for A, or we call it non-uniform. So this shows that, hey, we have a non-uniform, take note of that, velocity, but our acceleration is constant. So we have a constant, or we can say uniform acceleration. And so we are going to analyze this particular system based on a particular type of graph, which is called a velocity time graph. So we're going to be given a one case scenario where we have our velocity time graph, and in our velocity time graph, take note that the velocity here is measured in meters per second, and this is in the east direction, and in here we have our time, which is measured in seconds. And we have one case scenario where we are starting at a particular velocity here and we just boom increasing from there. And now the question is this: how are we going to bring our particular first equation into play? How are we going to analyze our first equation? And take note of this, Now, there are a couple of things to keep in mind. One way is to go backwards to determine the position time graph of this particular system, which is in this case represented as our position time graph, where we need to find what is the total displacement of this particular system, or move further, which means that we need to find the acceleration time graph. In this case, we need to determine what is the acceleration, what is the constant acceleration. So first step here is we need to focus on this particular part here, which means we need to find the area, in this case under the curve, like what we talked about on our previous video. And so the area under this curve here is going to be analyzed by the following. We have this whole region to focus on all the way to this side. So we have all this space to analyze, and to analyze all this space, we need to break this into two parts. So one part will be based on our triangle, which is seen right here, where this is our area, or I'm going to put a particular arrow here, area of a triangle, and this other region here is seen to be the area of a particular quadrilateral. In this case here, it's going to be either a square or a rectangle, we don't know. So let's get our specific things in place. So take note that for we to get our total displacement, we need to be able, or to find our change in position, we need to be able to not only take into account the area of our triangle, but also add our area of our specific quadrilateral. And so once we are able to get this, we'll be able to analyze this in detail. Now, take note that the area of the triangle is base times height divided by 2. And so since we know that half base times height is what we need in order for we to get the area of a triangle, and also the area of a particular rectangle is, in this case, length times width. So those are the two things to keep in mind in terms of what are the areas in here. So length times width. And so let's look at the following. First is we need to find our height of our triangle. So our height of the triangle is based on the final velocity and the initial velocity. So therefore, the final velocity minus the initial velocity gives us our change in our specific velocity here. And in this part here, we're able to come to a conclusion that our base is, on the other hand, with respect to time. So in here, we have our final time, and we have our initial time. Therefore, our base here is from here to here, which is our time final minus our t initial, which is our change in time. So therefore, our change in the position is going to be expressed now as, in this case, we are expressing in terms of velocity and our time, where our base, take note of this, is our time change, and our height of our triangle is our specific velocity final minus velocity initial. Take note of this to be our velocity, not our speed. So on the other hand here, our specific area of our rectangle, in this case, is now focusing on our final initial velocity. Take note of that. And we are going to subtract it from 0, which is the starting point. So therefore, we just have our initial velocity only. And that is going to be multiplied, in this case, initial velocity by our change in our time. And so once we have these two taken care of, our next step is to be able to do the following, expand our specific change in time into the bracket. And so therefore, in here, our change in position, which is our displacement, is equal to, take note of, our v final, or in this case, v final velocity change in time minus v initial times change in time. And take note that all this is divided by 2. And on the other hand here, we have plus v initial times our change in time. And so therefore, we can also break this down easily in here by just playing around with this. Therefore, in this case, our change in displacement is, take note of the following. We can just put our 2 here, multiply by 2, and so we have our common denominator, which in this case is going to be all this to be 2. And so where on this side, we have v final change in time minus, in this case, v initial change in time plus 2 times v initial change in time. Take note that these two, they are common, so therefore what we are left with is our change in our position to be equal to v final times change in time is going to be plus or added to v initial change in time, or divided by 2. Now, once we have this taken care of, our next step is to factor out our change in time, and therefore we have our first equation, which is expressed as our v final plus our v initial, all divided by 2, and this is all multiplied by our change in time. Take note that this almighty equation that we have here is not accounting for the acceleration. So acceleration is not present, or you can say it is independent of the acceleration. And take note that v final plus V initial, in this case, all divided by 2 is the same as our average velocity. So you can also re-express this here as average velocity times change in time is equal to our change in our displacement. So that is how you're able to find our first equation. And on our next video, we're going to talk about the second equation, where we're going to introduce the acceleration part, which is right here, and then incorporate it into another formula in our way to generate our new equation. So I hope you found this really informative. Please hit the comment down below. Let me hear your thoughts about this particular first step, which is creating our first equation. But that way I can talk to you all soon. Stay smart as always and believe in yourselves.